Hello everyone, welcome to Harsh IT Lab, and in this video we are finally going to see how the layer 4 protocol works in its full glory. The protocol data unit in layer 4 is known as segment, and there's a different type of protocol that guides this segment through the network. And the two most important protocols in layer 4 PDU are TCP and UDP. And in order to do the transmission on the internet, the TCP IP protocol typically chooses either TCP or the UDP based on the application requirement. And in order to understand which is selected when, we need to study how the transport layer protocols works. Don't let the name fool you, as TCP/IP is an umbrella term which contains the protocol TCP and UDP. And the key difference between TCP and UDP is that TCP is a feature-rich protocol which provides a variety of service like bit error, congestion, prevention, and error recovery, while UDP is the fastest one because it does not do all that. TCP stands for Transmission Control Protocol and is defined in RFC 793. It is also known as connection oriented protocol because it first initiates the connection before transmitting the actual data, and after initiating connection it generates something known as port number. A port number is a much more specific addressing system. It is a 16-bit field, and when combined with IP address, it makes the IP address more unique by subdividing it into application-based address or protocol-based address. And the combination of an IP address with a port number is known as socket. And just like the IP addresses, port number is also classified by IANA into three main ranges. If a port number lies between 0 to 1023, then these port numbers are called well-known port number. And further from that, if port number is between 1024 to 49151, then it will called user port or registered port numbers. And finally, from the port number 49152 to the maximum 16-bit value 65535 is known as ephemeral port number. The distinction of port number is based on its use case. The well-known system ports are assigned with a stricter review process and is tied to a specific application. Following it, user and ephemeral port are much loosely assigned, which means that it can be used by a system depending on data. We can also understand the need of well-known ports, as after remembering a list of most commonly used port, we can use these to identify the connection a device makes with the server and understand that which protocol is being used. And at once, a IP address can be assigned multiple port numbers depending on the applications running on it. Both of TCP/IP protocols uses a feature known as multiplexing using port, which is a facility that allows receiving host to choose the correct application for which the data is destined, all on the basis of port number. A list can easily be found on internet for the most common port numbers available, or I will be posting it on my community tab also. And after understanding it, let's see how the TCP actually establish connection. The establishment of connection by a TCP protocol is also known as three-way handshake, in which a PC tries to communicate with web server using one of the ephemeral ports that we just understood, which lies between 49152 to a maximum of 65535. And this initialization of connection via host is known as synchronization and sequencing, and in networking term it is called SYN message. And after getting this message, the web server responds to the same IP and port number combination with its assigned well-known port, which lies between 0 to 1023. This reply message is called synchronization and acknowledgement message, and in abbreviated form it is called SYNACK message. And by reviewing this message on any packet sniffing software, we can determine what kind of protocol the web server is using to communicate with host, or what kind of application is running on the host itself. And the final process in TCP connection establishment is the sending of an acknowledgement message by the host to the web server, assuring it that it received its SYN-ACK flag message. And after this three-way handshake, the actual data transmission take place. But TCP protocol also has a method to ensure that the connection is terminated successfully and the complete data transmission takes place. And to do so, it does a four-way handshake. The four-way handshake is also initiated by PC by sending an acknowledgement finish message, which is abbreviated as ACK-FIN message. And when received by the server, it sends an acknowledgement message as well as an acknowledgement finish message itself. And after receiving these both message by the PC, it finally sends a single acknowledgement and the connection terminates. And after a successful connection, now let's move ahead and see how TCP provides reliable data transfer and error recovery. It does so by initiating a sequence number. This segmentation is the process of assigning a special number to a chunk of data, telling the web server that it initiated the data transmission, keeping the sequence number in mind. But before understanding how sequencing works in TCP, let's get our fact clear about TCP first. This sequence number is a 32-bit field and is the most significant byte of the number that is sent first. A sequence number counts the byte rather than the packet itself. So it means that between two sequence number there might be a few packets or a few thousand packets, as it is determined by the number of bytes or data contains within the packet. The sequence number is consist in the header and is the first byte in the data. And if the first packet does not contain any data, it still needs to be sent, as it marks the upcoming of the next byte of the data. The TCP connection is a bidirectional connection in nature, which means that either a PC or a host can determine the initial sequence number. And after getting enchanted with all the required knowledge, let's now jump into how the sequencing works. It starts right after the three-way handshake. For this example, let's consider that the host or the PC initiates the sequencing with the web server. And for the ease in understanding purpose, let's assume that the sequencing starts with number 1, and depending on the number of bytes, the consecutive sequence number are determined. So let's be specific here, and the number of bytes will be 299. So when the web server receives this data with the sequence number 1 and 299 bytes of data, it sends an acknowledgement request, and the acknowledgement request consists of an acknowledgement number, which when received by the PC becomes the next sequence number. So here in our case, the first 299 bytes of data is received by the web server, and when it replies the acknowledgement, it gives the acknowledgement number 300. And when PC receives the acknowledgement of 300, it will start sending its next chunk of data, which will be of another 299 bytes, which add up to a length of 599. And when server receives this another 299 bytes of data with sequence number of 300, it generates another acknowledgement packet. And when the web server receives this another 299 bytes of data with an sequence number of 300, it will then forward an acknowledgement with the acknowledgement number 600. And the acknowledgement of data by adding 1 byte in the overall length of data is known as forward acknowledgement. So in this case, the forward acknowledgement is when the server receives 299 bytes of data, it generates an acknowledgement by adding 1 to 299 bytes, which will be 300. Same with the second message, when it receives a overall length of 599, it generates an acknowledgement by adding 1, that is of 600. This data transmission continues until we are at a state of four-way handshake, that is a state of correction termination. By sending a request with acknowledgement number 600, the PC expects to receive the data which is of length between 600 to 899 bytes. But in case where the data gets lost and the PC does not receive, in that case, the web server resends the acknowledgement message telling host to resend that sequence again. And this is how this sequence number helps to mitigate losses in transmission of data. Continuing with sequence number, in order to improve the efficiency of the network, a web server does not need to send acknowledgement for each time the data packet is received. In this case, the web server uses windowing. Windowing is the process of acknowledging multiple data chunks at once. Let's apply windowing in our example. In the first transmission of data, the sequence number was 1 and the number of bytes was 299. After that, the web server acknowledges it with acknowledgement number 300. So after that, the PC sends multiple streams, for example, two streams of data with the sequence number 300 and 600 consecutively. So after receival of these two chunks of data by web server, it acknowledges both by sending a single acknowledgement of 1200. And in order to receive the multiple chunks of data by web server, the web server has to tell the PC first that it is willing to receive the data chunks up to an acknowledgement number of 900. So when sending the first acknowledgement, it adds another field known as window field with a window size of 900. And this window size keep changing depending on how much a network is congested or the receiver or any network device in between transmission has exhausted its buffer overflow. And in case of that, the window sizes automatically decrease until the buffer clears for the further packet. A buffer is the small address space on the networking device in which it stores network packet for the further processing. This is all we need to know about TCP. And now jump straight into UDP protocol. UDP stands for User Datagram Protocol and is a much faster, minimalist, and connectionless protocol. By being connectionless, it provides no reliability, no windowing, no reordering, or any form of error control. The only thing that it provides are source based, port based multiplexing, and a checksum to ensure that data is not tampered with. It is great in use cases where the data loss is tolerable. For example, in YouTube video, if you right click on video and click on the option stats for nerd, you can see that while receiving a video feed, your device drops multiple frames in between, and the frames drop are the frames left. There is no need to regather all those dropped frames because we have progressed in the video. Think what will happen if the video transmission uses the TCP protocol. The all dropped frames aligned with upcoming frames, making the video a gibberish mesh. Until now, we have seen how the flow of data happens. But what in case if we duly want to restrict the flow of certain data? We can do so by first applying the different type of packets using their port numbers or the protocol used. Identification of certain packets can be used for dropping these selective packets as well as for application of quality of service. The quality of service is the special treatment of certain packets based on the priority or the nature of the protocol itself. We will study quality of service in our upcoming videos, and today our task is to take a look on the identification and dropping of packet. So to identify a packet, we use ACLs, which stands for Access Control List. The access control list are the rule which filters the network traffic depending on the parameters or criteria we set. And after creating an access list, we apply this access list onto an interface depending on the direction which we want to filter the packet. The direction may be inside a router or to the outside a router. Just by configuring an access list does not means that it will block the packets. We have to configure it on the per interface basis. The access list come in various forms like standard access list, extended number list, named access list. Formally, the ACLs are called IP ACLs and is primarily divided into three major types. The first is standard number list, second is extended number list, while the third is named access control list. Both standard access list and extended access list are bound to a number. The values between 1 to 99 and 1300 to 1999 belongs to the standard numbered access list, while the values between 100 to 199 and in between 2000 to 2699 belongs to extended number access list. Standard access lists are pretty basic in nature as they can only filter network traffic based on the IP address itself, and instead of using a subnet mask to denote a portion of IP addresses, we use the wildcard mask just like we used in OSPF. A wildcard mask is the inverted subnet address. That is, instead of zeros, we use 1, and instead of 1, we use 0 here. So suppose a subnet address of 255.255.255.255, which will become all ones in 4 octets, and after converting all ones into zeros, we get 0.0.0.0 as the wildcard mask representing the same subnet address. Now to form a standard access list, we have to pass a command that is accessed-list with a number between 1 to 99 or from between 1300 to 1999, followed by a permit or deny statement followed by the IP address itself. If we filter out a single IP address, we need not to enter the wildcard mask. However, a range of IP addresses can be filtered out if we use the wildcard mask with a network address. We can also enable the logging feature in the ACL by adding a log keyword at the last of the command. After that, it will generate a message every time the packet gets permitted or denied. One thing more to remember after configuring and applying an ACL, that all ACL comes with an implicit deny logic at the last. For example, suppose if we want to permit a specific IP address, the IP addresses other than the configured is automatically get denied, and this phenomena is known as the implicit deny of an ACL. By this logic, if we want to specifically deny a single IP address, After passing the argument of denying that a specific IP address, we also need to pass another command on the same access list with the instruction permit any to enable the transmission of all other IP addresses communication. We have already discussed the working of a standard IP access list. It is such a basic thing. And now we are at the discussion of extended ACLs. The syntax of extended numbered IP access list are quite identical, at least up to the permit or deny keyword. But unlike standard access list, it requires three matching parameters, which are the IP protocol type, the source IP address, and the destination IP address. Hence gives us more granular control over how we want to shape our network traffic, which means that we can filter the network traffic depending whether it is a TCP packet or an UDP packet. This protocol utilizes the complete benefit of port allocating system, as it can allow or block network packet destined to equal, less than, greater than, or in between, and finally not equal to the specified port address. Extended numbered access list uses a number ranged between 100 to 199 or between 2000 to 2699. As I have told earlier, its syntax is as follows: access hyphen list followed by a number from the just specified range, then followed by a permit or deny, followed by a protocol number, followed by a protocol name that may be TCP, UDP, or ICMP, followed by a source IP address. And if the source IP address is a network address, it will be followed by its wildcard mask, followed by a letter EQ, NE, IT, GT, or range, in which EQ stands for equal, NE stands for not equal, LT stands for less than, GT stands for greater than, or range stands for a range between two numbers, which will be followed by a port number. And all these things will be repeated for the destination address as well, which is the destination IP address, the destination wildcard mask, and with all these EQ, NE, LT, GT range followed by a port number. And right after this audio video, I will post a image contrasting the differences between an standard and an extended IPACL. So make sure to check out my community tab on YouTube. And before discussing the named access list, let's take a look between the differences of standard and extended ACL. As we know that standard ACL does not provide us many criteria controls, so it need to be placed as close as possible to the destination, otherwise it will block the important required network traffic. While on the other hand, in order to improve the efficiency, an extended ACL should be placed as close as the possible to the source of packet, because in order to drop a packet, it has to pass all the criterias of an extended access list. Another thing that be kept in mind, that the number followed by access hyperlist in the command does not matter, as we can put a maximum of two access lists per interface, one for incoming traffic and the other for outgoing traffic. What I'm trying to say, that no smaller number or a larger number access list will exceed each other in terms of traffic comparison. And now let's proceed towards named access list. The named access list comes with several benefits from the numbered access list. The first benefit is the self-explanatory. That is, instead of using numbers, we use the names, which make it easier to remember behind the reason of blocking the traffic. All the parameters of numbered access list must be passed into a global command, which means that in order to delete a specific parameter, we had to delete the access list completely, while the name access list enables the use of subcommand, and by the help of subcommand we can delete or insert an individual line of the parameter inside a already built standard named access list, and hence the command for configuring a named access list varies slightly. So to configure a named access list, and command IP space access hyphen list space extended space the name of the access list must be passed, and after passing the command we are into the ACL configuration mode, and after that it is quite similar like the previous list. We have to start passing parameters starting from permit or deny, followed by the type of protocol, followed by the host IP address, their wildcard mask with equal, less than, greater than, not equal, or range of port addresses, and the same for the destination address. That will be destination IP, destination wildcard mask, and the equal, less than, not equal, greater than, or range of the port addresses. And just like the previous access list, only configuring a access list does not enable the blocking of the certain packet. In order to make it work, we have to apply on the interface. In order to apply any of the access list, the command is same, that is IP access hyphen group with the name or number of the access list, followed by whether we want to apply it inside or outside with the keyword in or out respectively on the selected interface. The only way to master an access list is to check for practice questions on the internet or on the YouTube. It is a very simpler concept, as a single requirement can be fulfilled using multiple different configuration. And after making a few questions, I am sure that you will feel confident in configuring access list. And the time has come to wrap up our session. Thanks for joining in. Thanks for joining in, and see you in the next one. Bye.